So this video will be in our final chapter in AP Chemistry, and that is electrochemistry. So in this chapter, what we're going to do is we're going to study how we can take chemical potential energy and convert it into electrical energy. And this really does form the basis of a lot of our society right now. So whenever you think of batteries, what's happening is we're taking a chemical reaction and we're harnessing that driving force, the free energy change in a chemical reaction, and we're using it to cause electrons to flow through a wire. We create what's called a potential difference between the two terminals of the battery. So we're going to see how that's done. We'll see how concentration and how the chemical reactions affect the voltage of these batteries. And I hope you enjoy it. This topic, this whole unit is one of my favorite units. So before we talk about these galvanic cell things, what we have to do is we have to go back and kind of revisit redox, because redox equation or reactions are what we use in these batteries. And so what I'm going to use for this video is this model, this model reaction. So we're going to have 10 2 plus aqueous, and we're going to react that with solid zinc. And it's going to go one direction. So it's going to form 10 solid, and it's going to form zinc 2 plus ions. Okay, and if you remember, this is a pretty straightforward example, but we use these oxidation numbers to determine what's oxidized, what's reduced. So the 10, the oxidation number of 10 is plus 2. For elemental zinc, it's 0. For elemental 10, it's 0. And for zinc, it's plus 2, this zinc ion. And so here we would have an oxidation occur. So that's our oxidation. And then here, I'm going to put this up top here. Okay. We go from plus 2 to 0, and so it reduces the oxidation number, and so this is our reduction. And when we were balancing these equations before, what we were doing is we were looking at what's called the half reactions. Okay, that we would use. So in this one, we would say, okay, I have 10 2 plus, and I need to go to 10 solid. In order to have that happen, I need to gain 2 electrons. So electrons are the only things that get exchanged in these reactions. And so we would say that this is a reduction half reaction. Okay, so we're only showing like half of the whole process. So this is the reduction half reaction. We'll be using these half reactions a lot in this chapter. We're going to be studying this a lot. And you'll see why in just a second on the next slide. And then for the zinc, solid, and it's going to zinc 2 plus. And to do that, I had to lose 2 electrons because I lost electrons. Electrons are going to be a product, and so this is my oxidation half reaction. Now, I think at this point it's a valid question to ask, well, how do we know it doesn't go the other way? How do we know that zinc's not reduced and tin isn't oxidized? And we'll talk about that when we talk about cell potentials. But for right now, what I want you guys to be able to do is to look at a redox reaction and to break it up into these half reactions. Now here's the cool thing. If this occurred in one beaker, so if we had our solid zinc and we had a solution of tin ions, this would occur within our beaker. But what we can do is we can separate these two half reactions. Okay, and there's this driving force to go from zinc to zinc 2 plus, tin 2 plus to tin. This is a spontaneous reaction as written. And so what we'll do is on this side we'll say, okay, here I'm going to take solid zinc, and I'm going to form zinc 2 plus 2 electrons. And so what's going to happen is the zinc is going to go from solid zinc, and it's going to start to enter the solution. And as it does that, these electrons are going to flow, because on this other side, what's happening is I have tin 2 plus, and it needs 2 electrons to form solid tin. So I would have the tin 2+ ions, and they would start latching on to the tin metal. And so these electrons would, would go here, and then they would be kind of absorbed by this tin 2+ as it goes to form tin metal. And so what we would have on this side is we would have this mass. The mass of the tin would slowly decrease over time because I'm losing metal and they're forming ions in solution. This will start to gain mass over time because I'm taking these ions, they're gaining 2 electrons, and they're forming the metal. Now, we give a special name to these 2 sides, okay? And it's based on the processes that occur. So we would say this side is our anode. So you guys might have heard these words. This is our anode, and this other side is our cathode. Okay, a way to remember this is, and this is a little mnemonic, you might think it's kind of corny, but an ox, red cat. Okay, so I think ox red is supposed to be a color, but anyway, anode oxidation reduction occurs at the cathode. So use it if you want. I think it's a good mnemonic, but it reminds you of what processes occur on both of these terminals. And so we would always have, in this case, we always have electrons going from our anode to our cathode. Now, at this point, you might see kind of a problem in that we're pumping positive ions on this side and we're losing positive ions on this side. And so after a while, we're going to have kind of a net positive solution. We have a net negative solution, and so these electrons, they'll be attracted to this positive charge. So they won't be able to kind of get away. There's going to be no driving force anymore to cause them to go from one side to the other. So what we have to do is we have to essentially complete the circuit. And so this is what the salt bridge is going to do. So this salt bridge is going to have all kinds of ions in it, but let's say that it has sodium sulfate ions. So say that we have like this sodium sulfate. Obviously, there's like 2 sodiums per sulfate. And this will be kind of in a gel, right? And so we'll have all these kind of ions in here. But what can happen is as the zinc ions in a solution, a sulfate could pop out and they can neutralize it. Okay? And as these tin ions leave solution, I'll get sodium ions coming out to neutralize that solution, to neutralize the charge. I'm not talking about acid-base neutralization, I'm talking about charge neutralization. So in a sense, I have electrons that go over, come over here, and then they kind of go back to the other side in this sulfate ion. Okay, and that forms a complete circuit. And again, the driving force of this is the spontaneity of this reaction. It's the decrease in free energy that occurs as zinc goes to form zinc 2+, and as tin 2+ goes to form tin ions. Okay, it's a delta G of this oxidation reduction reaction. So what we can do is we can use these oxidation reduction reactions, so we can use the free energy change of them to drive electrons from one side to the other. And in the process, we can put like little lights in here, little light. Okay, we put the lights, we can put motors, we can put our cell phone, we can put all kinds of stuff in these batteries and use this decrease in free energy to do work. Okay, and so anyway, our lives are much simpler, arguably better because of all this, and so we'll talk more about this in class.